All right, hi, 8 Purple. So soon to be freshman, let's talk about our weather maps that we looked at yesterday and just recap why we have seasons. So this first one was cloud cover. There's not much going on here. There's just two things that I like to point out. One is that Africa and Australia both have these periods of time where there's like virtually no cloud cover, just totally blue skies for a long stretch of time. Everywhere else seems to have pretty decent cloud cover. Or on average, I guess, for most of the year. Our next map is a map of precipitation. So the interesting thing here is how you have this band of precipitation that's pretty constant year round surrounding the equator, and sometimes it goes a little bit north or south, but it's pretty much always there, except for when you get to Africa. Again, they're kind of getting starved for water. And then you also have some pockets of water right here in Indonesia, and then also in the eastern seaboard. That must be during hurricane season. And so you get these little patterns. One thing I wanted to show out here, or that's starting to show, is how there's this vertical motion that occurs. So we're starting to see some up and down, north and south movement with these weather patterns. Here it's much more clear. This is soil moisture, which is very closely tied to precipitation, and they have this up and down patterns. You have some very dry conditions in northern and sometimes southern Africa, as well as in Australia and in the southwest United States. The next one is vegetation, which is also probably very closely tied to soil moisture. And you can see some really lush conditions in like northern Russia and then even up in Canada and Alaska at certain times of the year. This is pretty stationary, dry, not much vegetation going on in the deserts over here. Look at the rainforest, that's almost consistent year round. There's almost no change there. So that's kind of some interesting patterns. Average surface air temperature. So this is what it would look like if you record all of the temperature at different latitudes. The one really cool thing here is just how far those cold temperatures come down in the north compared to how far they come up in the south. So if you look at the south, during their winter, that cold comes up pretty far. It gets to the Arctic Circle, but it's nothing compared to how far the cold comes down in the northern hemisphere. So during our winter, that cold stretches almost all the way down to the Tropic of Cancer. Look at how far those cold temperatures get. That's the reason for that is because of all of the land mass that's concentrated in the north compared to the south. So most of this is all water, right? And so that water doesn't give up its heat or doesn't cool down as easily as land mass does. So because of that, we experience more dramatic temperature swings in the north. And then lastly, this is a pretty constant, this is solar radiation. And so because this isn't really weather patterns, this is more exactly what the sun is doing to our planet. It's a constant band or nice straight lines across the different latitudes. What's interesting here is you might see every now and then some gray bands that form in the north and south poles. And that's a result of the times of year where they are not pointed towards the sun. So during our winter, when the north pole is pointed away from the sun, it gets zero light for a couple of months. And so it's not going to get any solar radiation. And the same is true in the opposite end of the year for the south. All right, a couple of important annual dates. I want to talk about solstices and equinoxes. The winter and summer solstice and the fall and spring equinox, these mark the start of the seasons. So the winter solstice is the beginning of winter and the spring equinox is the beginning of spring. Solstices are the time of year when the sun reaches its highest or lowest point in the sky. So its highest point would be summer, its lowest point would be winter. It's marked by the longest and shortest day. Just so you know what this means, solstice derives from the word sol, which is sun, and sis from sistere, which is Latin meaning to make stand or to be stationary. And this is because the sun's path doesn't appear to change for a long period of time. So let's go to our model here. There it is. I'm going to go to our model, and I want to show you what happens during the solstices. So here we're in winter because we know we're in winter because the Earth is tilted, or the northern hemisphere is tilted away from the sun, so that southern hemisphere is getting direct sunlight. And if you look at this, the angle, the sun's altitude, it's about 26, 27 degrees starting at the end of November. And if we go to the end of December, now it changes just by about 2 or 3 degrees. So an entire month, it's just 2 or 3 degree change in the sun. And if we go to the end of December, I'm sorry, the end of January, it's still not that much of a change. Now we're at 30 degrees altitude. That's like 3 degrees. But let's fast forward a couple months into the spring. So here we're going to start at the beginning of March. And in March, we're at 41 degrees. And if we go 1 month later, just 1 month to the beginning of April, we're now at 53 degrees. So a change of almost 12 degrees happens during the springtime. So our sun, the path that the sun is taking is dramatically increasing during these spring months, during late winter, all of spring, and all of spring. And then once you get to summertime, the same thing happens. That sun's altitude, that path that it takes across the sky, it doesn't really change all that much. It kind of stays there. And then in the fall, it drops very, very, very quickly as we go into winter. Equinox. So what's interesting about the equinox is that this means equal night, equinox. So this is the time of day when the day length times are equal all across the globe. So everywhere gets 12 hours of daylight and 12 hours of nighttime. This is showing it's very slow, but you can see that the seasons change. This is a year time lapse of the sun's rays hitting Earth at different angles. Now this kind of gives the impression that the sun is moving up and down like a flashlight, but that's not what's happening at all. This line here is called the solar terminator, and it separates the daytime from the nighttime as a pretty distinct line. It happens during dusk and dawn. If you were to take this straight line on a sphere and map it on a two-dimensional map, it would become a curved line like this. So here is what that solar terminator looks like during the winter solstice. And you can see, if I could pause this, it'd be easier, but you can see the distance between the daytime up here is very short compared to the daytime down here. That indicates that we have short days and long nights in the northern hemisphere, which is true during winter. The opposite happens during summer. Now we have a big stretch between our solar terminators, so we have a long day and a very short night. And then the opposite is true in the southern hemispheres. During the equinoxes, they look the same because everywhere on Earth gets 12 hours of daylight and 12 hours of darkness during the equinox. So we've kind of looked at this from a couple models. One model would suggest that the Earth like wobbles north and south, but we know that that's not true. The Earth doesn't do that. The second model suggests that maybe it's a sun that moves up and down like a flashlight shining on different parts of the globe, but we also know that that one isn't true. And so we get seasons because of a different impact, right? So the reason we have seasons is because the Earth is revolving. So this model is our truest model. This one shows how the tilt of the Earth and its revolution around the sun is a cause for the changing angle of light, of sunlight that we get. So here, when the northern hemisphere is tilted towards the sun, we get high angles of sunlight. It's very concentrated, right? It's a very concentrated beam. And so that results in higher temperatures, and we call that our summer. And then as we progress through the year, that angle is still fixed this way, and that sunbeam gets spread out, and so the energy does not get to be absorbed, or it warms up a larger area, or the energy is spread out over a larger area, and that results in cooler temperatures. So to summarize those three concepts, we say this about our seasons. The Earth is tilted on its axis. That tilt is always oriented towards Polaris in the same direction, and the Earth revolves around the sun. These three things cause changes in the angle of sunlight hitting Earth's surface, and that results in different seasons. Okay, thank you so much. Thanks for watching, and if you have any questions, make sure to email.